In this tutorial, we're going to go through the examples in Chapter 6, the beam approximation. We are going to start first by introducing two tools in Mathematica. The first one is rules, and the second one is how to solve a differential equation, so that we can utilize those tools in the next examples. So the first thing I would like to talk about is rules. Rules allow you to evaluate an expression for a particular value for the variables without changing the nature of the expression. For example, if I have y is equal to x squared, and I want to have y always equal to x squared without assigning a value to x, but at the same time I would like to know what's the value of y for a particular value of x, I can say find y when, using the rule, open curly bracket and close the curly bracket, inside the curly bracket assign a value to x. You assign a value to x by writing x and then an arrow and give it a value. For example, I would like to know y when x is equal to 2. So this is a rule of assigning 2 to x without really changing the value of x and without really changing the value of y. So shift enter will tell me that y when x is equal to 2 is equal to 4. This does not change the value of y and does not change the value of x. So I'm going to print y when x equal to, and then print y, and then print x. So first I say y is equal to x squared, and then when x is equal to 2, find y, without really changing the value of x and without really changing the value of y, and then find y, and then find x. When I press shift enter, y when x is equal to 2 is equal to 4. Y itself is x squared and x is x because I haven't really given any value to x. So this is the first tool that we're going to use, which is assigning rules to expressions, or utilizing rules to assign values to expressions for evaluation purposes. The second thing is, how do you solve a differential equation? Let's say I have the second derivative of y with respect to x squared is equal to 5. I would like to solve the differential equation that tells me that y prime, the second derivative of y with respect to x, is equal to 5. Let's say this is my differential equation that I would like to solve. Now, this is a second order differential equation, which means I need two boundary conditions. I can solve it without assigning any boundary conditions. I could say differential equation solve, open square bracket. This is my differential equation, but I have to put 2 equal. I'm just going to start from scratch. And I have to say I would like to solve for y in terms of x. So the differential equation says that second derivative of y with respect to x as a function of x is equal to 5, but I have to use double equal. And I'm solving the differential equation for y. Y is what I'm looking for, and it's a function of x. Shift enter, and it gives me a rule that y is a function of x, and the function is equal to 5x squared over 2 plus a constant 1 plus x multiplied by a constant 2. You can also put some boundary conditions to find those constants right away. So if I, instead of instead of just using this equation, I'm going to use a list of equations. Because I'm going to use a list of equations, I'm going to put curly brackets. I'm going to add the boundary condition. Let's say the boundary condition is that y as a function of x, as a function of 0 is equal to, and I'm putting 2 equal sign 0. So let's say the first boundary condition is y of 0 is equal to 0, and the second boundary condition is that y prime of L, or of 0, the first derivative of y with respect to x when x is equal to 0 is also equal to 0, which basically gives me that the two constants are equal to 0. Shift enter, and I get a new solution that incorporates the boundary conditions. I could change the boundary conditions as much as I want. I could say that the y prime, or the partial y by partial x when x is equal to L is equal to 0. Shift enter, it gives me a different solution. And this is how I solve a differential equation. Okay, so usually I define a function. What I'm looking for is a function y of x, and this is the function that I'm looking for. It's a function y of x. Okay, so let's now solve the questions in chapter 6. We have a cantilever beam given Young's modulus, and the beam is 5 meter. The height of the beam is 0.5 meter and the width is 0.25 meters. We have a load of 125 kilonewton applied at the free end. We want to draw the contour plot of the stresses along the beam. And we need to sketch the principal stress directions at the top fibers, the bottom fibers, the neutral axis, and at quarter of the height of the beam at the support. We need to also draw the vector plot of the displacement of the beam. So if you watch the lecture, you'll find the hand calculations, how to solve this beam using hand calculations. Now we're looking on how to solve this beam using Mathematica. Now I'm going to start from scratch. And first I would like to define my moment. My moment function is equal to EI multiplied by the first derivative, actually the second derivative of y with respect to x. I will put with respect to x twice. This expression means the moment is equal to EI dy by dx twice, which is d2y by dx squared. The shear is equal to EI multiplied by d y by dx 3 times. The theta is equal to EI multiplied by d y of x with respect to x. The distributed load on this beam is equal to 0. Now, in order to apply the boundary conditions, the boundary conditions are usually given in terms of y, theta, shear, or moment. So, the moment on the left end, I will call it m1, and I will say that the moment on the left end is equal to the moment when x is equal to 0. The moment on the right, I'm going to call it m2, is equal to the moment when x is equal to L. Notice that I'm using the rules without really evaluating, so I'm just evaluating the moment when x is equal to 0 without really calculating, without really changing the value of m. Shear is the shear at the left end is equal to the shear when x is equal to 0. The shear at the end, the second end, is equal to the shear when x is equal to L. The rotation at the left end is equal to the rotation when x is equal to 0, and the rotation on the right is equal to the rotation when x is equal to L. And finally, the deformation or the deflection y on the right is equal to y of x is equal to the function when x is equal to 0, and y2 is equal to the deflection on the right when x is equal to L. Now I can solve my differential equation. I will store the solution inside a variable called s equal differential equation solve, and curly brackets, I'm looking for a solution for y in terms of x. Now, the differential equation itself is EI multiplied by d for y by dx power 4. So I'm going to write it as y 1, 2, 3, 4 of x. That's equal to d for y by dx. This is equal, don't forget the two equal signs, equal to q, and q in this case is 0. I would like to put the boundary conditions here. The boundary conditions for this cantilever beam is that on the left, the rotation is 0, the deflection is 0. On the right hand side, the shear is equal to the value of is equal to 125 kilonewton, so I'm going to put 125, and the moment is equal to 0. So when I press shift enter, I get a solution. I get the y is a function of x, and this function is equal to negative 125 3l multiplied by x squared minus x cubed divided by 6ei. So solve the differential equation and applied the 4 boundary conditions to give me a function of y. Now this is a rule. I have not really replaced y. I'm just saying that the solution to this is a function of x. Now to store or to extract this, I'm going to call it the displacement solution. So the displacement solution is equal to y when I grab this rule. I want to utilize this rule. Now this rule is put inside a curly bracket. So it's a list. So I'm going to utilize this, which is stored inside S, and use the first row. Shift enter, and it tells me that the displacement is a function of x of this function. Or I can even make it in a simpler way and say the displacement is equal to y of x, utilizing s of 1, which is the solution, and that will tell you that y is equal to, or the displacement is equal to negative 125 3lx squared minus x cubed divided by 6ei. And now I can utilize the moment is equal to the moment after I'm going to use full simplify. This is equal to the moment after utilizing this solution. Shift enter, and you get that the moment is equal to negative 125 L minus x. The shear is equal to the full simplify. The shear, when I use this, the assignment of S. So the shear is equal to 125. I'm now going to input the parameters of the problem. So E is equal to 2 1, 2. So E in the problem is given as, let's see, 20 gigapascal, so 20 and so now I have changed it into units of kilopascal, simply because the reason why I'm using units of kilopascal is because I used the force of kilonewton. So I'm putting a note here, units of kPa. This is Young's modulus. B is equal to, the width of the beam is equal to 0.5 meters. The thickness is equal to 0.5 meters. The moment of inertia, and I can't use I because this is reserved for another variable in Mathematica, so I use II. And similarly for E, I can't use E because it's reserved for another function in Mathematica. That's why I'm using EE. So II is equal to B multiplied by T cubed divided by 12. S sigma 11 is equal to negative the moment multiplied by x2 divided by I. So this is the value of S11. S12, the shear S12, is equal to negative VQ divided by I B. So I need a value for Q. Q is given as T over 2 minus x2 multiplied by B multiplied by T over 4 plus x2 over 2. So now I have a value for S11 and S12. I'm going to form my matrix of stress. My matrix of stress is a 3 by 3 matrix that's made out of S11, S12, 0, S12, 0, 0, and then 0, 0, 0. So this is the matrix of stresses, and you can, if you shift enter, let's view it in matrix form. Let's full simplify it as well. So full simplify S matrix and view it in matrix form, and you get this is S11, S12, S12, and everything else is 0. I'm going to utilize the von Mises function that I created a long time ago in chapter 3. I'm going to copy it and paste it. Here, shift enter. So this is the von Mises function, and the von Mises stress is the von Mises function of this stress matrix. Shift enter, and you get that the von Mises stress is equal to this, and you can utilize full simplify if you want. And you get this. Now it's still a function of L, so we will have to put a value for L, and so we can perhaps input L here. L is equal to 5, and of course EI, which is the variable that we used here multiplied in M and V and theta, EI is equal to EI is equal to the value of E multiplied by the value of I. Shift enter, and here is the value of my von Mises stress, and it's only a function of small x and capital X2, and the small x I'm using to represent capital X1 in the problem. Okay, so the first thing is how to plot contour plot for all this. Contour plot. I would like to plot the contour plot of sigma 1, which is S11. I would like to draw it for x between 0 and 5, and x2 is between negative 0.5 to negative 0.25 to positive 0.25. That's the height of the beam. And I would like to give it a label. The label is plot. Label is S11 in kPa. Shift enter, and here is the value S11. I need the contour labels to be I think true, and I would like also to use aspect ratio, automatic aspect ratio, and here's the beam, and you can make it slightly bigger, or you can put an aspect ratio of, let's say, 3. Let's see what this gives us. Aspect ratio of 1/3, and you get this plot of the S sigma on 1 in kPa. If you want to do plot sigma on 2 across the beam, put S12, and the plot label is S12 in kPa. Shift enter. Here is your sigma on 2 in kPa. If you want to plot the von Mises stress, we called it von Mises stress. Copy, paste, shift enter, and here's the von Mises stress in kPa. We also would like to plot the displacement of the beam. So displacement of the beam is given by a vector u, where u is equal to a vector I'm going to utilize, because I'm drawing a two-dimensional vector plot. So the horizontal displacement, as if you look at the actual problem, it's equal to negative x2 multiplied by the partial displacement with respect to x, and the vertical is equal to the displacement. Shift enter. Let's see what I get. This is the first component, and this is the second component. I can now plot the vector plot of the displacement when x changes from 0 to 5 and x2 changes from from negative 0.5 to 0.5, which is the thickness of the beam. X 0.25 to 0.25, the thickness of the beam, and I will give it a label, vector plot of displacement. I will use an aspect ratio of 1/3. Shift enter, and here's the displacement of the beam, the vector plot of the displacement of the beam. Now what we're asking for is the principal stresses and the principal stress directions at when x1 is equal to 0. So I'm going to evaluate. So now I've stored the stresses in my S matrix. Shift enter. Here's my matrix of stresses. I would like to find the eigenvalues and eigenvectors at specific locations. So these locations are, I'm going to write eigensystem of the S matrix. First location is when x is 0 and x2 is equal to 2.5, or negative 0.25, and put this in matrix form. I'm going to copy this and do it multiple times. When all these times is when x is equal to 0, x is equal to negative 0.25 divided by 2, x2 is equal to 0, x2 is equal to positive 0.25 over 2, and finally at the top fiber of the beam is when x2 is equal to 0.25. Shift enter, and you get all your the values, principal stresses, and the directions. at each location. And you can draw and here are your directions, and you can draw the directions vectors on your beam. And if you look at the solution in your textbook, you will see a sketch of these eigenvalues and eigenvectors on the beam. The second problem that we're going to cover is a similar problem, but we're doing the same thing, but instead we're doing the beam has a distributed load and it's simple beam. So I'm going to go here and copy everything here and go through it again. I'm going to copy this and paste it here, and I'm going to start from scratch. So I'm going to quit all the values to free all the variables. So again, this is the moment, this is the shear, this is the theta, the rotation. But notice that I put here EI, but I shouldn't put EI. The rotation is only equal to dy by dx. So it did not affect the previous problem because it was equal to 0. The boundary condition was equal to 0 anyway. So the moment is equal to EI dy by dx, d2y by dx squared. The shear is equal to EI d3y by dx cubed. Theta is equal to dy by dx. Q, the distributed load, is equal to negative 125 kilonewton per meter. The height of the beam is 0.5 and the width is 0.25. M1 is the moment on the left, M2 is the moment on the right, V1 is the shear on the left, right, rotation on the left, rotation on the right, displacement on the left, and displacement on the right. Solve the differential equation of equilibrium. The boundary conditions for this problem are different. The boundary conditions are, this is a simple beam. Simple beam means the moment on the left is 0 and the deflection on the left is 0. The moment on the right is 0 and the deflection on the right is 0. Solve for y in terms of x. Then, I don't need this, then capture the solution in the displacement y of x utilizing the solution, then capture the moment after utilizing the assignment of the solution, and capture the shear after utilizing the solution. Shift enter. Here's the solution for the displacement, here's the moment, and here's your shear. And then the displacement. Then we need to input the other variables in the problem. The length is equal to 8 meters. The B is equal to 0.25 meters. 0.25 meter. The thickness of the beam is given as 0.5 meter. The moment of inertia is B multiplied by T power 3 divided by 12. Young's modulus is given as 20, and I'm going to use kPa, so 1, 2, 3, 1, 2, 3, so 20 gigapascal, and S11 will be given as negative the moment multiplied by x2 divided by I. Q, similar to the previous problem, is equal to the area multiplied by the height between the area and the centroid of that area, between them. So the height is between the neutral axis and the centroid of the area, which will be equal to 3 over 4 plus x2 over 2. So S12 will be equal to negative the shear multiplied by Q divided by I divided by the width of the beam. and our stress matrix will be equal to S11, S12, 0, S12, 0, 0, 0, 0, 0. Let's full simplify our stress matrix and view it in matrix form. And here's the stress matrix given in matrix form, function of x1, x small, I'm using small x for x1, and x2, so the horizontal displacement, the horizontal coordinate and the vertical coordinate. And I'm going to utilize the von Mises function that I have created in the previous chapters. Shift insert. This is the von Mises function that I created, and this is the von Mises function for the stress matrix. Shift enter, and here is the von Mises function of x1, which is small x, and x2, capital X2. Okay, so now I'm going to plot, contour, plot the von Mises stress when x is between 0 and 8, that's the length of the beam. X2 is between negative 0.5 to negative 0.25 to 0.25, that's the height of the beam, and then the neutral axis is in the middle. The contour, the contour labels display the numbers. The plot label, you have to give it a label. The plot label is von Mises stress kilopascal, and the aspect ratio, let's say 1/4. Shift enter, and here's the I'm gonna just make it bigger. Here's the von Mises stress. You can see the maximum von Mises stress is in the middle. This is a simple beam. The maximum von Mises stress is in the middle here, at the top and the bottom fibers, and there's no difference between the tension and the compression. You get the same number. I'm going to copy and paste this, and instead of von Mises stress I will put S11 and S12. Shift enter, and indeed this is my I need to change the plot label. This is S11 and this is S12. S11 compression at the top, tension at the bottom. S12, this is the shear, and the shear is 0 in the middle for a simple beam. If you remember your shearing force diagram, 0 in the middle, and shear is closer, you have higher shear closer to the supports, and the values of the stresses in the shear, they're much smaller than the actual S11, than the longitudinal stresses. We are missing we would like to also plot the displacement of the beam. Basically the arrow is showing how the beam is displaying. So I'm going to take the displacement vector. I need a horizontal displacement and a vertical displacement. The horizontal displacement in beams is given by negative x2 multiplied by the displacement multiplied by dy by dx, and the y, I'm storing it in a variable called displacement, and so this is dy by dx, and the vertical displacement is y. And now I'm going to have a vector plot of the displacement from x to 0 and x2 from negative 0.25 to 0.25, and the label will be displacement, or u. Shift u vectors. Shift enter, and nothing was there was no output, because instead of y I should put actually displacement. Still, so I'm going to just view u in matrix form just to see why I'm not able to plot it. And as I look here, it's a function of x and x2 and also EI, which the problem is I have not evaluated EI, I have not given EI a value, so I'm going to say EI is actually equal to the Young's modulus multiplied by II by the moment of inertia, and now shift enter and you should get your displacement of the beam. And you can see it's a simple beam. Displacement is 0 at the support and the displacement is maximum in the middle. We have a few more problems that we're going to go through. They are very similar to all this. In this problem, this is a beam under axial load. The displacement function of the beam has only one horizontal component, and what we're looking for is that horizontal component along with the stresses along the beam. The differential equation of equilibrium is a function of only the horizontal component of the beam, which we call U1. So you should revise before you go ahead and watch this tutorial. You should watch the description of the beam, the description of the solution using hand calculations. So we have a horizontal beam with a distributed load of 125 kN. The load is 0 at this location and 125 at this location, and the load is a compressive axial load. The displacement boundary condition is horizontal displacement here is 0, horizontal displacement here is 0, and the height and width and length of the beam are given here. Young's modulus is 20 gigapascal, and we're going to ignore, as usual, the effect of Poisson's ratio. And we need to find the displacement function of the beam. And sigma 1, 1. Okay, so first, the function that I'm looking for is u of x, which is the horizontal displacement. The boundary conditions are going to be the horizontal displacement on the left, which is u of x when x is equal to 0, and the displacement on the boundary condition on the right will be given as the displacement function u of x when x is equal to L. Don't forget, I'm starting a new problem. I'm going to quit the kernel just to start from scratch so that I don't have any variables stored already in any of those symbols. The distributed load, I'll call it Q normal, is equal to 125 multiplied by x divided by L. I'm going to solve the differential equation. The differential equation is actually equal to EA multiplied by the second derivative of the displacement with respect to x, and this is equal to negative Q normal. And you should revise the watch the tutorial or watch the lecture to see how this differential equation was derived. The boundary conditions are u1 is 0 and u2 is 0. We're looking for u as a function of x. Shift enter, and here's the solution. The solution is a function of x, and this function is equal to 125 L squared x minus x cubed divided by 6 EAL. So I'd like to store this solution in u, so I'm going to utilize u. U is equal to u of x after I utilize this solution. And here I stored my function. S, we can say epsilon 1, 1 is equal to du by dx. S11 is equal to Young's modulus multiplied by epsilon 1, 1. Perhaps I should start giving values to all those variables. Young's modulus is 20 gigapascal, again using kPa. the area of is equal to b multiplied by t. B is equal to 0.25, t is equal to 0.5, sigma on 1 is equal to e multiplied by epsilon on 1, and the length is equal to 5 meters. Shift enter, and I should have started from scratch. I'm going to quit the kernel again, quit, shift enter, and here's the solution. Another thing is that perhaps I should always start with clearing all the variables, and shift enter, and that finally gives me the solution for sigma on 1 as a function of EA. So I have to say what EA is, because I use the variable here called EA. EA is in fact equal to Young's modulus multiplied by the area. And here's the solution for S11. The displacement vector is equal to u and 0. The horizontal displacement is u and the vertical displacement is 0. Now I can plot my vector plot of the displacement. The small x varies from 0 to 5. Capital X2 varies from negative 0.25 to 0.25, which is basically, I should perhaps maybe use negative t over 2 up to t over 2. Plot label. This is the displacement vectors. Shift enter. Sorry, I should put here the displacement, the shift enter, and here's the displacement of the beam. And you can see at this end the displacement is 0, at this end, the other end, the displacement is 0, in the middle the maximum displacement. I should maybe use a better aspect ratio, 1 over 3, or here's a better aspect ratio. I'll make this slightly bigger. And for the stress, the contour plot of S11 will tell me how the stress is varying on the beam. So I'll copy this, and the label I will call it S11 in kPa, and I have to plot contour labels true, otherwise the numbers don't make any sense. Again, 750 kPa, 500 to 150, negative 1250. In the next problem, it's exactly the same, but the difference is the boundary condition. So basically, all I have to do is just copy everything. Everything is the same, but the difference is that the boundary condition here is given in terms of the stress, and the stress here is 0. So I will make sure to start from scratch so that I don't inherit any values. And I'm going to change the boundary condition. The boundary condition here at this point is in fact given in terms of sigma 11, which is equal to dy of x with respect to x when x is equal to L. Because at this point, this is equal to, that's the stress. So this is because the stress at this point is equal to Young's modulus multiplied by epsilon on 1. Epsilon on 1 is equal to partial ux by partial x. So partial ux by partial x at the location x equal L multiplied by EE. So this is S2. So I don't really need EE here, but the boundary condition is that S2, the stress on the second end, is equal to 0. Because it's equal to 0, I don't even need the value EE. Just say that this is the partial u by partial x when x is L is equal to 0. Everything else is the same. Shift enter, and you'll get now a different shape for the displacement. The displacement here is much higher because the displacement here is 0 and the stress is tension everywhere. And compare with the previous problem, the displacement is only maximum in the middle. And it makes sense because here we restrained both ends, but in the second problem we restrained one end and allowed the other end to freely move. So we're going to solve the last problem in your chapter, which we also solved in the online lectures. We have this beam with a distributed force and a distributed body load with a value of rho multiplied by the area, and we have it has a vertical load hanging at the bottom with a value of p. The length is 4 units. The radius changes from 2 units at the top to 1 unit at the bottom. So first I'm going to write r as a function of, or first I'm going to clear all the variables. I'm going to write r as a function of x. R is equal to 2 minus x1 over L. I'm going to put a value, well, maybe I don't need the value for L, so I'll just leave it 2 minus x1 over L. So this is the value of R. The area, I'll leave it as A, is equal to pi multiplied by R squared. Shift enter. So this is the value of the area. I'll leave Young's modulus without evaluating it for now. And the area at the end, at the bottom end, is going to be equal to A when x is equal to L. Sorry, when x1, I'm using the variable x1. So the area is equal to, the area at the end is equal to A when x1 is equal to L. And here's the area at the bottom end is equal to pi. Now I need to solve the differential equation of equilibrium that says, if you now read your notes, now I'm looking for a horizontal displacement, or the displacement u with one component as a function of x1, because I'm using x1 as my main variable. So I need to write my differential equation in terms of x1. If you look at your notes, the differential equation of equilibrium is given as follows. E, which is Young's modulus, and I'm using EE because, remember, one E, capital E, is utilized for something else in Mathematica. So the differential equation is given as follows. E multiplied by area multiplied by D, or U double prime, partial 2U by partial x1 plus EE multiplied by D area with respect to x1 multiplied by U du with respect to x1 plus rho multiplied by the area. This is equal to 0. So this is the differential equation of equilibrium. The boundary conditions are given in terms of u when x is 0 equal to 0. The displacement at the top end is 0, and the second boundary condition is given in terms of the stress. Young's modulus multiplied by the strain, which is du by dx1 at the bottom, which means when x is equal to L, this is equal to the value of the force divided by the area at the end. Shift enter, and indeed I get a solution, and I am going to store the solution. I'll call u is equal to u once I utilize, or u of x, once I utilize this solution. Shift enter, indeed here's the displacement of the beam. I can and if you compare this, this is exactly the answer that you have in your book. So this is it for the for this chapter, and in the next chapter we're going to introduce different ways or numerical methods for which you can solve differential equations of equilibrium without those restrictive assumptions on the displacements. We're still going to have some assumptions, but they're going to be a little bit more or less restrictive, and will allow us to utilize different numerical methods or to explore possible solutions to the differential equation of equilibrium.